The maximum electric field a material can withstand without the occurrence of breakdown is called dielectric strength. The dielectric strength of air is 3 kV per millimeter. That means air can tolerate at best the electric field of 3 kV per millimeter. If more than this electric field is applied to air, then air becomes ionized, where you can find a positive ion and negative ion. That means air becomes a conductor if electric field exceeds this. The dielectric strength of air is about 3 kV per millimeter, but is the largest charge a 0.8 centimeter radius metal sphere can hold if sparking is not to occur in the air surrounding it. The sparking occurs because if the electric field exceeds this, then the air becomes positive and negative ion. So if the conductor is a positive charge body, it will attract the negative ions. If the conductor is a negative body, it will attract positive ions. So thereby the conductor become neutral and sparking also occurs during this time. This discharge is called corona discharge. So for the problem, the electric field must be 3 kV per millimeter. Radius of the conductor is given and we are considering it is air. So 3 kV per millimeter is 1 by 4 pi epsilon 0. Actually it is 1 by 4 pi epsilon A q mod by r square. Since epsilon A is nearly equal to epsilon 0, then we can solve q mod is equal to this much. Polarization. This is the dipole moment per unit volume. The limiting process is included so that the p vector is a point function. That means the p vector is defined at a point. The polarization is related to the electric field. P vector equal to epsilon 0 chi E vector. This equation is applicable for isotropic and linear. If it is isotropic, then P vector, E vector are in same direction and chi may not be constant. If it is linear, then for weak electric field, chi is independent of electric field, so chi is a constant then. So for linear and isotropic dielectric, chi is a positive constant. The electric displacement vector of isotropic dielectric is d vector equal to epsilon 0 E vector plus P vector. If you put P vector here, then the equation becomes d vector equal to epsilon E vector, where epsilon is equal to epsilon 0 1 plus chi. This chi is called electric susceptibility and epsilon is called electric permittivity of the dielectric. So from this, the dielectric constant or the relative permittivity or the dielectric coefficient is epsilon by epsilon 0, that is equal to 1 plus chi. Dielectric constant of air is 1.00059. So the chi of air is 0.00059. A homogeneous medium is that for which the properties do not vary with position. Means what property you observe here, the same property will be here, the same property will be here. If it is isotropic, then the properties are same in all directions. If you see this way, what the property you observe, if you see this way, you will observe the same thing. For isotropic, the properties are same in all directions, and homogeneous, the properties are same at all points. The capacitance or capacity of a water tank, we understand that the water storing capacity. The water storing capacity of a water tank doesn't depend or doesn't vary with the amount of water present. Similarly, the capacitance of a conductor, that measures the charge storing capacity. Similarly, the capacitance of a conductor should not depend on the amount of charge present in the conductor. The charge of a conductor is directly proportional to the potential. So we can write Q is equal to constant into V, or we can write potential is equal to a constant into Q. This 1 by C constant is called elastance. This constant 1 by C, that is the reciprocal. C is here capacitance and 1 by C is called elastance. So the equation 1, this is the capacitance of, in equation 1, C is the capacitance of a conductor or of an isolated conductor. The capacitance of an isolated conducting sphere, to find it, consider a conducting sphere of radius r placed in an infinite homogeneous dielectric of permittivity epsilon. Let Q be the charge on the conductor. Then the potential of the conductor is 1 by 4 pi epsilon Q by R. So the capacitance of the conductor is C is equal to Q by V, that is 4 pi epsilon into R. If the conductor is in vacuum, then the capacitance is 4 pi epsilon 0 into R. What is the radius of a conducting sphere in vacuum having capacitance 5 microfarad? The conducting sphere is in vacuum, capacitance is 5 microfarad, radius is asked, radius is 1 by 4 pi epsilon 0 into C0. Putting this, we got 45 km. So a 45 km conducting sphere has a little bit capacitance. So this cannot be a practical use of such a big body having so less capacitance. That is why we have to construct a small body having large capacitance. This small body consists of some conductors, any shape doesn't matter, separated by insulator. This arrangement is called capacitor or condenser. So we use the capacitor for two purposes. One, for storing charge and energy, and hence energy, and other purpose, the capacitor provides reactance. The capacitor provides reactance to AC. AC means alternating current. So because of this property of the capacitor, we can reduce AC without producing heat. without producing heat, we can reduce AC because the capacitor has the property that is called reactance. The capacitance of a spherical capacitor. The spherical capacitor, the inner conducting sphere has charge plus Q. The outer conducting sphere has charge minus Q. Here Q is greater than 0. The capacitance of such capacitor is 4 pi epsilon. Epsilon is permittivity of the dielectric that fills the gap between the two conductors. And so the capacitance is 4 pi epsilon AB by B minus A. A and B, they are the inner radius and outer radius. If the inner conducting sphere is connected to earth, outer conducting sphere or outer conducting spherical cell is given charge Q, then the inner conducting sphere will carry charge minus Q, and if the space between the two conductors it is dielectric of permittivity epsilon, then the capacitance is 4 pi epsilon B square by B minus A. Again, A, B are the inner radius and outer radius. Now the capacitance of a parallel plate capacitor. A parallel plate capacitor consists of two conducting plates of equal area parallel to each other, like so. Think this is a conducting plate. This is a conducting plate. Below another conducting plate. The two conducting plates are parallel to each other. The two conducting plates are parallel to each other. They have the same area and the separation is D. This separation is D. The plate area is say A, and the space between the plates is a dielectric of permittivity epsilon. So this is shown in this 2D figure. The upper plate is given charge plus Q. The lower plate is given charge minus Q. Here Q is greater than 0. So that is the upper plate positive, lower plate is negative. All the positive charge on the upper plate comes to lower side. All the negative charge on the lower plate goes to upper surface. This charge distribution occurs to ensure the electric field At this point inside the conductor has to be 0. Also the electric field at this point inside the conductor has to be 0. To ensure this, such a distribution of charge is possible. So upper plate charge Q, lower plate charge is minus Q. The electric field between the two plates is E vector, that is perpendicular to both the plates and it directed from positive plate to negative plate. If D is very small compared to the lateral dimension, means length and breadth of each plate, then the electric field between the two plates is uniform. If we ignore the fringing effect means the electric field just outside or at the edges of the plates, the electric field at the edges of the plates are like this. The electric field at the edges of the plates are like this. Similarly on the right side also this way. This way. This is called fringing effect. If you ignore the fringing effect, then we assume the electric field between the two plates is nearly constant. So the electric field by the upper plate is sigma by 2 epsilon. The electric field by the lower plate is also sigma by 2 epsilon. The total field is now sigma by epsilon. Sigma is the magnitude of surface density of charge on each plate, which is equal to Q by A. Now the A plate is at high potential, B plate is at low potential. A plate potential is VA, B plate potential is VB. So VA minus VB, that is E into D. This is only applicable in case of uniform electric field. And putting the value of E, we get VA minus VB is equal to QD by A epsilon. So the capacitance of the capacitor is C is equal to Q by VA minus VB. Q is greater than 0, that is the magnitude of charge on each plate. So the capacitance is A epsilon by D. If the space between the two plates is vacuum, then the capacitance is epsilon 0 A by D. The capacitance is independent of the thickness of this conducting plate and the thickness of this conducting plate. Whatever may be the thickness of the conducting plate, the capacitance remains this. In a parallel plate capacitor with air between the plates, each plate has an area. The distance between the plates, the capacitance is asked. If the capacitor connected to 220 volt, the charge on each plate is asked. A given, D given, capacitance, it is the air. So the capacitance is epsilon A into A by D. Epsilon A is nearly equal to epsilon 0, that is the permittivity of vacuum. Epsilon A is the permittivity of air. So putting the value, we got the capacitance 17.7 picofarad. Then the charge on the capacitor is CV. CV is 220 volt. Then this gives 3894 coulomb. 3894. This will be 3894 picocoulomb. 3894 picocoulomb, because picofarad is here. Picocoulomb. Capacitance of a cylindrical capacitor, C equal to 2 pi epsilon L by Ln B by A. B is the outer radius, A is the inner radius. The cylindrical capacitor is looking like this. The cylindrical capacitor, this is one cylinder which is a conductor. Inside there is another conductor which is also cylindrical. This radius is B and this radius is A. This space is dielectric of permittivity epsilon. The length of the cylinder is L. The length of the cylinder is L. So the capacitance is 2 pi epsilon L by Ln B by A. Consider n number of capacitors of capacitances C1, C2, Cn connected in series. This series group of capacitors is connected across a battery that provides a potential difference of V. The left plate of the first capacitor, since connected to battery positive, so it is positively charged, let it is plus Q. The right plate of the last capacitor connected to battery negative, so it is negative charge, minus Q. And we can prove the first capacitor, the right plate will be minus Q charge, second capacitor, left plate is plus Q charge, and so on. That means the charge on each capacitor is same and is Q. The potential difference across the first capacitor is V1, the potential difference across the second capacitor is V2, the potential difference across the nth capacitor is Vn. V1 is equal to Q by C1, V2 equal to Q by C2, Vn equal to Q by Cn. So V is equal to V1 plus V2 plus Vn. This series group of capacitors is equivalent to a single capacitor. Of this equivalent capacitor, the first plate is this plate, the second plate is this plate. So the charge on the capacitor is Q and the potential difference across the capacitor is V. Let the capacitance is C. So V equal to Q by C. Hence 1 by C equal to 1 by C1 plus 1 by C2 plus up to 1 by Cn. That is C equal to 1 by C1 plus 1 by C2 up to 1 by Cn. In this series grouping, the effective capacitance is less than each of these capacitances. Consider n number of capacitors of capacitances C1, C2, Cn connected in parallel. This parallel group of capacitors is connected across a battery that provides a potential difference of V. The potential difference across first capacitor is V. The potential difference across second capacitor also V. The potential difference across nth capacitor is also V. That means the potential difference across each capacitor is same. But the charge on the first capacitor is Q1, the charge on the second capacitor Q2, and charge on the nth capacitor is Qn. So Q1 equal to C1V, Q2 equal to C2V, Q1 equal to Cnv. This parallel group of capacitors is equivalent to a single capacitor. The first plate of this effective capacitor is this plate plus this plate plus this plate. So the charge on this plate is Q equal to Q1 plus Q2 plus Qn. Similarly, this plate of the effective capacitor is this plate plus this plate plus this plate. So the charge on this capacitor is minus Q, that is minus Q1 plus minus Q2 plus minus Qn. The effective capacitance is C, its potential difference V, charge is Q, so Q equal to CV. Here Q is, and this Q, if we compare, then you will get C equal to C1 plus C2 plus Cn. That means the effective capacitance is more than each of these capacitances. Three capacitors of capacitances 2 microfarad, 3 microfarad, 6 microfarad are connected in series. Total capacitance we have to find. The potential difference across each capacitor we have to find. The supply voltage is 240 volt. So these are the capacitors connected in series. The charge is same on each capacitor. The potential difference is different. This is the effective capacitor. Since series combination, C equal to 1 microfarad. The effective capacitance is 1 microfarad. V is 240 volt. So the charge Q is CV, that is coming 240 microcoulomb. The potential difference V1 is Q by C1. C1 is 2 microfarad. So V1 is 120 volt. Similarly, V2 is 80 volt. V3 is 40 volt. If you add V1, V2, V3, it will become 240 volt. Three capacitors of capacitances 2 picofarad, 3 picofarad, 6 picofarad connected in parallel. What is the total capacitance of the combination? Determine the charge on each capacitor. Supply voltage is 250 volt. The effective capacitance is 11 picofarad. Here the potential difference across each capacitor is same, that is 250 volt. So the charge on the first capacitor is C1V. Similarly, charge on the second capacitor is C2V. The charge on the third capacitor is C3V. Energy of a charged capacitor. When we buy an uncharged capacitor from the market, the first plate was neutral, means the charge is 0. The second plate is also neutral, the charge is 0. If it is connected to the battery positive and this is connected to the battery negative, so this plate become negative charge, this plate become positive charge. It is possible the battery will draw positive charge from the right plate and it will give the positive charge to the left plate. Actually, electrons move from this left plate through battery to the right plate. So the charging of capacitor, that will take some time because battery always draws small amounts of charges from one plate to other plate. Let during charging at the time t, the charge on this plate is minus q and the charge on this plate is plus q. Now the potential difference between the two plates is V. The capacitance is Q by V. In the time from t to t plus dt, in the time from t to t plus dt, more dq charge will move from this plate to this plate. So the work done against electric field is V dq. V means this left plate potential minus the right plate potential. So putting V equal to Q by C, then dW, this is the work done against electric field when charge dq is transferred from this plate to this plate. So the total work done to make the capacitor charged to Q, that means Q charge is transferred from this plate to this plate. Total work done is Q square by 2C. This work is stored in this electric field as the potential energy. Final potential difference across the capacitor is Q by C. So putting this V, we get three formula for this potential energy or the work to charge the capacitor. The energy density of the capacitor is the potential energy divided by the volume of the region between the two plates. The volume of the region between the two plates is AD. So it is half CV square by AD. For the parallel plate vacuum capacitor, C is epsilon 0 A by D. Then the energy density is half epsilon 0 E square. So the energy density is independent of the capacitance. The formula says wherever there is electric field in vacuum, there is an energy density half epsilon 0 E square. A 10 picofarad capacitor connected to 60 volt battery, how much electrostatic energy stored in the capacitor? C given, B given, energy stored is half CV square, it is coming 18 nanojoule. We use dielectric in the capacitor. Why we use? What is the effect of dielectric on the capacitor? This is a vacuum capacitor, uncharged. The capacitance is epsilon 0 A by D. Now this vacuum capacitor connected to battery. As a result, here the charge is Q0, here minus Q0. The electric field is now this much. The energy stored in the capacitor is this. The capacitance is this. Now in the presence of the battery, let us insert a dielectric slab. Since the battery is connected, there is no change in V, but the charges on the capacitor, that changes. The electric field in this vacuum also changes compared to the previous stage. Now the electric field in the vacuum gap is E0 dash, and in the dielectric the electric field is E. This is E0 dash by K. K is the dielectric constant. Then we can find the relation between Q and Q. Now the capacitance is C is equal to epsilon 0 A by D minus B plus B by K. This formula arises C is equal to Q by V. Then C by C0 equal to Q by Q0 equal to E0 dash by E0, that is equal to U by U0, that is coming D by D minus B plus B by K. C0 was the capacitance, Q0 was the charge on the capacitor, E0 was the electric field in the vacuum gap, U0 was the energy stored in the capacitor before the dielectric slab is inserted, C is the capacitance, Q is the charge on the capacitor, E0 dash is the electric field in the vacuum gap, U is the energy stored in the capacitor in the presence of dielectric slab. Again as earlier, in vacuum the capacitance is. Now connect this to battery. If we remove the battery, the charge, the electric field, the energy stored, everything remains same as the previous stage. Now let us insert the dielectric. The charge remains same as the previous stage. The electric field in the vacuum gap is also same as the previous stage. Now the electric field in the dielectric is E equal to E0 by K. Then the capacitance is epsilon 0 A by D minus B plus B by K. Then C by C0 equal to D by D minus B plus B by K, that is equal to V0 by V, that is equal to U0 by U, that is more than 1. More than or equal to 1. C is the capacitance, V is the potential difference, U is the energy stored in the capacitor in the presence of dielectric, C0 is the capacitance, V0 is the potential difference, U0 is the energy stored in the capacitor in the absence of dielectric. A parallel plate, capacitor with air between the plates has capacitance, particularly with the capacitance if the distance between the plates is reduced to half and the space between them is filled with a substance of dielectric constant 5. K5, C air capacitor is nearly equal to C0, that is given 10 picofarad. Then the new capacitance is K epsilon 0 A, since the distance is half, so it is D by 2. In a parallel plate capacitor with air between the plates, each plate area given, the distance between the plates given, the capacitance is asked, capacitor connected to 150 volt, charge on each plate, and if a dielectric slab is inserted, then what will happen we have to discuss. The air capacitance nearly equal to the vacuum capacitance. So C by C0 equal to Q by Q0. In the first case, it is given voltage remain connected. Second case, voltage was disconnected. Already you know the formula. This is this type of formula applicable for battery remains connected, and this formula applicable for battery disconnected. A slab of copper of thickness B is thrust into a parallel plate capacitor, but the capacitance after the slab is introduced. So the upper is a conducting plate, the lower is a conducting plate, this is a conducting slab. Then we can cut the slab. We can cut the slab here and detach the upper part and the lower part, and we have to join the upper part and the lower part by a connecting wire. So two capacitors connected in series. So the figure will look like this is the upper capacitor, this is the lower capacitor. The two capacitors connected in series. This gap is X. So this is X. This gap is D minus B minus X. So this is D minus B minus X. This capacitance is epsilon 0 A by X. This capacitance is epsilon 0 A by D minus B minus X. So since they are connected in series, the effective capacitance is this. And in this equation, B has to be less than D. That means B has to be less than D only. If B equal to D, then this equation is not applicable. A slab of material of dielectric constant K has the same area as the plates of a parallel plate capacitor, has the thickness CD by 4. D the separation of the plates. The capacitance have changed after the slab inserted. B given. C by C0 is D by D minus B plus B by K. So the capacitance ratio is coming this. A 500 picofarad capacitor is charged to 100 volt supply. It is then disconnected from the supply and is connected to another uncharged capacitor 300 picofarad, and the electrostatic energy that is lost in the process. The first capacitor energy was this. When the two capacitors are joined, the common voltage is this much. So how the two capacitors are joined? The two capacitors are joined this way. This is one capacitor. This is the other capacitor. Then we join by the wires. We join by the wires. So the two capacitors have a common voltage. The two capacitors have a common voltage V. This common voltage is this much. Then final energy, this is the first capacitor final energy, this is the second capacitor final energy, they have a common V. So the energy lost is the initial energy minus the final energy. This much